Hello everybody. So that was the Paleozoic we just covered. So now let's have a quick think about the Mesozoic. So if you look, the Mesozoic was a time of continental breakup. So if we look down here, this was the state of affairs during the Triassic. So what have we got here? I know it looks a bit messy, but down here we have what's essentially Gondwana, and up here we have what's essentially Laurasia. So what are the bits that we can see? Well, this is North America right here. This is Europe, this is Asia, and this is Southeast Asia over here. So here we have South America. You can just see the South American west coast there. We have Africa here. You can see the northern coast of Africa there. We have India, located right here. Antarctica's here. And we have Australia there, with Papua New Guinea attached to the top right there. Okay, so you can see that's what we have at the start of the Triassic, and during the Mesozoic what's going to happen is we're going to develop a whole load of divergent plate boundaries, and it's going to slowly but surely tear these continents apart, and eventually we're going to end up with the individual continents that we can see here. And so this was the situation in the Cretaceous. So the Cretaceous is marked out by particularly high sea levels. You can see, for instance, that North America is bisected by these seas here, known as the Cretaceous Interior Seaway. We can see that Europe is nearly completely underwater. We can see that huge parts of Africa, large parts of South America, and well, that's about it really. We can see we've got India here, it still needs to move north, and Australia here still needs to break off Antarctica. But you can see by the time we're in the Cretaceous, we have all the major continents and we know where they're going to end up. So in terms of the early Mesozoic land masses, well, once again, it's a continuation of the Paleozoic land masses. We'll have these two huge chunks of crust, which are obviously going to be quite dry in the core and typically quite wet on the margins. So you're going to have lots and lots of essentially forest along the coasts, and in the cores of these pieces of continental crust you're going to get drier, more desert-like conditions. Okay. Now, in terms of the end of the Mesozoic itself, it's obviously marked out by the KT boundary. Okay, and this is the extinction event that destroyed the dinosaurs. So if we look at the diagram, the impact itself hit around here as part of the Yucatan Peninsula of Mexico. So it hit just on what is now the modern day coastline. So half the impact crater is in the sea, in the Gulf of Mexico, and half the impact crater is on land. But it's buried, so you can't really see it that well. And this was a particularly, nasty impact. Obviously, it threw huge amounts of material into the atmosphere, very fine material, which hung around in the atmosphere for many, many years. So you probably don't know, but when you put lots of very, very fine material in the atmosphere, when sunlight hits the Earth, that fine material reflects it back into space. And so what would have happened is global temperatures would have dropped very, very quickly. Very bad if you're a reptile. And so this obviously would have this also meant that plants had less light to photosynthesize. This would mean that plants would die, or at least they would become less productive. That means fewer plants, less food. So once again, if you're something like a reptile, like a dinosaur, you're in real trouble at this point. However, if you're a small, warm-bodied mammal who's perfectly safe, you can maintain your own body temperature, you can live on very, very small amounts of food for a very, very long period of time, well, in that situation, things look pretty good, don't they? So you can see how this impact would have led to the end of the dinosaurs. So in terms of life in the Mesozoic, well, life in the Triassic at least was relatively straightforward. We had the appearance of the very early mammals. Once again, very, very small. Mammals throughout the Mesozoic didn't really get very big at all. There are a few examples of bigger mammals, but on the whole, relatively few and far between. As you can see, we have the appearance of some very, very early dinosaurs here. And in terms of what we have these huge forests made out of seedless vascular plants and gymnosperms. Okay, so these aren't flowering plants like the trees we have now. So these are types of fern, types of conifer, for instance. That's what we have. And they make these huge, huge forests. And these huge forests continue all the way through to the Jurassic. Now in the Jurassic we begin to see dinosaurs establish themselves, and they start getting bigger and bigger and bigger. There's a couple of reasons for that. Number one, the environment dinosaurs are working in is very favourable to them. Okay, so if you're a reptile, you want warm conditions, and obviously plenty of food is helpful, and essentially you have warm conditions essentially near globally during the Mesozoic, and so that means conditions are suited perfectly to dinosaurs, and obviously the warm conditions would obviously help to produce, a very high yield when it came to plants, so there would also have been, significant amounts of food around. The other thing that helps to drive the increase in size that we see from dinosaurs is, of course, predators. So typically, if you're a dinosaur, one of the ways you get around being attacked is, well, you can cover yourself in spines, like a stegosaurus here, a big spiky tail. Or one of the other ways is you can just get really big. And so we begin to see dinosaurs beginning to get larger and larger and larger in the Jurassic. And one of the reasons they did this would have been to avoid predators. There comes a point when a predator is just going to look at one of these large dinosaurs and just going to go, no, too much effort. So you can see here we have a sauropod, don't know what type, so we'll say Diplodocus, and here we have ourselves an Allosaurus, a member of the theropod family, the same group that makes up the same group that includes Tyrannosaurus rex. However, as you can see, this is not a Tyrannosaurus rex because you can see it has very, very large digits on the forelimbs, and the shape of the skull was distinctly different. Allosaurus had these big bone ridges just above its eyes for protection. So looks very similar to T-Rex, but not quite the same. We also have the appearance of the flying reptiles. Okay, so these are essentially these transitional forms where reptiles are slowly transitioning into birds. As we move into the late Mesozoic, so Cretaceous, what do we begin to see? Well, we begin to see, number one, in some places, South America especially, we have the appearance of huge sauropods, massive ones, absolutely gargantuan. And so when it comes to the rest of the world, though, the sauropods actually start doing quite badly, and they start, retreating. Their numbers drop very, very quickly in the Cretaceous. So typically in South America, we have these huge sauropods, but in the rest of the world, the sauropods are being replaced by a group of dinosaurs called the ornithopods. Okay, and they're smaller, and but they move in huge herds, so they're smaller but more numerous. And think of them kind of like not think of them like gazelles, not the same size. Think of the way they act like gazelles. So they're moving in these huge herds, sweeping across the plains, eating everything they can as they go. And of course, these smaller herbivorous dinosaurs were perfect prey for animals like Tyrannosaurus rex, okay, and other smaller predators like Utahraptor, which is essentially the raptor that the Velociraptor in Jurassic Park was based on. Okay, just in case you want to know, Velociraptors were the size of about a good-sized turkey. All right, so yeah, not quite the same level of fearsomeness that you got from the movie, eh? Anyway, so you can see in the Cretaceous we still have these huge forests made of conifer trees and ferns, etc. But we also have the appearance of the flowering plants. And the flowering plants are going to outcompete the gymnosperms and the seedless vascular plants very, very quickly. And they're going to become the dominant species as we move into the Cenozoic. In terms of what we've got going on in the Mesozoic, obviously we have the age of the dinosaurs. It's a greenhouse climate, so it's very, very warm, as I mentioned earlier. Most of North America becomes a desert, once again, very advantageous if you are a reptile. And we see, obviously, the result of this, very thick layers of sandstone forming, especially in the western US. So as you move into the Cenozoic, well, we can quite clearly see by the Cenozoic, most of the continents are kind of where we expect them to be. They're not perfect, as we can see. Africa hasn't made full contact with Asia yet. India hasn't really, India is just, making contact with Asia. We can see Australia has still got quite a long way to go to reach its current position. Same for Papua New Guinea there. And we can see that South America and North America still haven't quite met. They will do though. They'll essentially make contact in the area of Panama. You can just see this string of very mixture of very thin islands and continental crust coming down here, and eventually South America will make contact with that. At that point you'll have obviously a land bridge between North America and South America, and you'll have animals capable of migrating that land bridge, and so North America, the animals can go south, and South American animals can obviously go north. In terms of what's happening with North America, we have the Laramide orogeny. This is part of one of the three orogenies that produce the Rockies. And obviously towards the end of the Cenozoic we have a very large northern hemisphere focused glaciation, which we refer to as the Ice Age, taking place. And that covered large amounts of northern Europe and huge amounts of northern North America in snow and ice. And obviously Antarctica also expanded, but not too far. So in terms of life during the Cenozoic, well, in the early Cenozoic we really see the mammals begin to establish themselves. As I said, initially the birds made the first move, but they were reasonably quickly outcompeted by the mammals. So in the early Cenozoic we see the bats, the rodents, the primates, the sloths, the whales, the hoofed animals, the marsupials, and we see the small horses all beginning to, number one, in some cases appear, and in some cases, in most cases, they will begin to diversify. So we'll see different numerous species beginning to appear from each family. Okay. By the late Cenozoic, what do we see? Well, we see the first humans appearing. We see organisms specialized for cold climates beginning to appear, because in the early Cenozoic, the conditions are somewhat similar to the late Mesozoic. However, the general trend throughout the Cenozoic is for a decrease in temperature, and eventually that gets us to the point where we end up having an ice age. So by the late Cenozoic we see, as I say, the first humans, and we see organisms specialized for cold climates. So we see organisms that have lots of fur, but we also see organisms that become very large. So we see huge bison, we see huge woolly rhinoceroses, we see huge woolly elephants. Okay, and essentially the reason they're becoming quite large is simply because a large animal is actually better at retaining heat. Yes, it requires more food to survive, but as long as it can find that food, it's actually more efficient when it comes to heat retention. So that's why we started to see these very large animals appearing during the last ice ages, simply because it was more efficient. Okay, so now we've got to think about the next part of this presentation, which is radiometric dating. So this is essentially using radioactivity in minerals contained within rocks to date the rocks. Okay? So, alright, so let's have a think about elements and atoms. So solid matter is made up of atoms. So I'm knocking on my desk, that's solid matter, made up of atoms. So every atom is an element. So if you remember elements, they're the things that we have in the periodic table. So things like nitrogen, carbon, oxygen, sulfur, etc. At present, there are 92 naturally occurring elements and 26 have been produced in labs. So that's 118 elements in total. Although I dare say by now it's probably 119, who knows. So each atom has a nucleus, that's the center of the atom, and the nucleus is made up from protons, which have a positive charge, and neutrons, which have a neutral charge. So you have these protons and these neutrons all put together, and they form this spherical body, which we refer to as a nucleus. Now, around this nucleus, you will have electrons, which are negatively charged particles, and they will orbit the nucleus, a bit like planets, a bit like the planets in our solar system orbiting the sun. Now, the thing is the number of protons and neutrons in your nucleus can change. So this is the situation that we have with an atom. So as you can see, in this case, we have a nucleus consisting of 1, 2, 3, 4 protons and 1, 2, 3, 4, 5 neutrons. Around this nucleus, we have the electrons orbiting. In this case, we have 1, 2, 3, 4, 5, 6 electrons orbiting around the nucleus. Okay. Now, we can't see them, but there's going to be a couple of extra protons on the other side. So this atom has a proton number of 6. Okay, so it has 6 protons in its nucleus. And this means it is therefore carbon. So the type of element you're dealing with is based on the number of protons in the nucleus. That's what tells us what element it is. So for instance, if you have 8 protons, you have oxygen. 26 protons is iron, and 79 protons is gold. That's essentially how we classify the elements. It's based on the number of protons in the nucleus. Now this is referred to as the proton number, and it's given the abbreviation Z. So here we go. So if we look at the periodic table, there's the proton number up here, and it says 6, that's carbon. As you can see, you look at any of the other elements. So we've got iridium down here, that has a proton number of 77. So in the nucleus, there are going to be 77 protons. Okay. Now, the number of neutrons is variable, but the number of protons will stay the same. So any atom that contains 77 protons in its nucleus will be iridium. Okay, so now we've got to think about what an isotope is. So an isotopes are very, very important. So the number of protons that an atom has in its nucleus defines the element. We just discussed that. However, the number of neutrons that a nucleus can have is variable. So this means that something which we refer to as the atomic mass, which is the number of protons plus the number of neutrons, can change. So if we have a look at this picture down here, what can we see? Well, this is a standard atom of hydrogen. 1 proton in the middle with 1 electron orbiting around it. However, we can also come up with deuterium, which is an isotope of helium. It still has 1 proton, so it's got to be helium. Okay, so 1 proton, helium. Must be helium. However, in this case, it's also got a neutron added to it. So the atomic mass is now 2, isn't it? 1 proton plus 1 neutron, atomic mass of 2. We have 1 electron still orbiting around the outside. Here we have another isotope of helium. It's called tritium. As we can see, in this case, we have 1 proton, so therefore it must still be hydrogen, sorry. So 1 proton must be hydrogen, and then in this case we have 2 neutrons attached to it. So the atomic mass is, of course, 3. 1 electron orbiting around the outside still. So these are isotopes of hydrogen. So you can see the number of protons is remaining constant. However, the number of neutrons is variable. And this means you're going to end up with different versions of an atom, different versions of an element that have slightly different atomic masses. And each one of these is referred to as an isotope. So here we go. So this is the case for potassium. So potassium has a proton number of 19. Here we go, potassium proton number 19. However, the number of neutrons in the potassium nucleus is variable. You can have 20, 21, or 22. And this means the atomic mass of the nucleus will vary. In the case of this one, it's 20 plus 19, atomic mass of 39. By the way, K is the abbreviation for potassium. In this case, neutrons, 21 plus 19, that gives us an atomic mass of 40. Number of neutrons, 22. Number of protons, 19. Atomic mass of 41. So you can see that the number of protons is remaining constant, so they're all potassium, but the number of neutrons is variable. So each one of these is an isotope of potassium. Now, some isotopes are stable, so that's great. However, some isotopes are going to be naturally unstable. and they will fall to pieces. And this process of an isotope falling to pieces is called radioactive decay. Okay, so one of the classic examples of that is, of course, uranium-235. Okay, as we know, uranium is naturally very, very unstable. It will break down through radioactive decay, and it will keep breaking down until it reaches what's referred to as a stable daughter isotope. Okay, so it will keep breaking down. So the parent isotope, the uranium, will decay and decay and decay time and time again until it eventually achieves a configuration which is stable. So uranium-235, the parent isotope, will decay to lead-207, which is referred to as the daughter isotope. It is stable. It will not decay any further once it reaches lead-207. So what's the difference between stable versus unstable? Now, we're going to give this a very general overview. Okay, so we have a nucleus. So in a nucleus, we have two different forces. We have what's referred to as the strong nuclear force, and that's trying to pull the protons and neutrons together. So it's trying to pull the protons and neutrons into a tighter and tighter and tighter space all the time. At the same time, the protons are positive, aren't they? So you know what happens. If you take the positive ends of two magnets and you try and push them together, well, they naturally repel each other, don't they? So that means an atom's nucleus is a balancing act between these two forces. The strong nuclear force that wants to constantly pull the nucleus into a smaller and smaller and smaller space, and the electrostatic repulsion which constantly wants to push the nucleus apart. So the nucleus, as you can see, is essentially working on a very, it's a balancing act. And if one of these forces becomes dominant over the other, the nucleus is naturally going to start falling to pieces, isn't it? So this is, these are some of the controlling facts of why a nucleus is stable. So when we have our essentially our unstable isotope, now remember, this is going to be the parent isotope up here. In this case, it's uranium-235. So that means the atomic mass is 235. You see this number down here, 92. That's the number of protons. That tells us it's uranium. So 92 protons means it's uranium, but the atomic mass is 235. Okay? So I'm not going to do the mental arithmetic. I don't know how many protons it takes to get from 92 to 235. I'm sure you can crack that one for yourselves. Grab your phone, do the calculation. Anyway, so what we have here is what's referred to as a decay chain. So it's very, very rare that the parent isotope will decay straight to the daughter isotope. That's very, very rare. What it normally has to do is it has to go through several intermediate steps. And you can see, so the uranium here is going to break down to thorium, and then it's going to bounce around through lots of different options until eventually it gets here and it reaches lead-207. And that's the daughter isotope, the stable daughter isotope. Okay? Now you can see in between these different isotopes, you'll see there's lots of these letters. So we've got beta here and alpha here. Okay? Now these are different types of radioactive decay. So when your isotope is decaying, breaking down, it doesn't just decay in one way. There are several different ways in which it can decay, so the parent can decay to eventually achieve the daughter via the decay chain. Remember, most radioactive elements will have a decay chain. Okay, so if we look at this diagram here, all right, what can we see? Well, actually, do you know what? Let's ignore the diagram for just 1 second. Sorry, let's go to the text. So let's think about how we can achieve balance. So remember, the reason our nucleus is trying to rip itself apart is because we have one force that's trying to pull the nucleus into a smaller space, and we have another force that's trying to push the nucleus apart due to repulsion between the were just between the positively charged particles, whose name completely protons. That's it. Between the protons. Cripes, that was a close one. So how essentially can our nucleus achieve balance? Well, if our nucleus is trying to pull itself into a smaller and smaller and smaller space, well, the thing to do is simply to add more protons. As you add more protons, the repulsive force gets stronger, and that will start to balance out this force that's trying to make the nucleus get smaller and smaller and smaller. Done. The other option is if your nucleus is trying to get bigger and bigger and bigger because the electrostatic repulsion is winning, well, the simple thing to do is throw out some protons. Kick enough protons out until the electrostatic repulsion and the force that's trying to pull the nucleus tighter and tighter and tighter are balanced. And then once again, you've achieved harmony, and it's all done. So that's the basic process of radioactive decay. You'll just either want to throw stuff out of your nucleus or add stuff to your nucleus to achieve a stable nucleus. And once you have that stable nucleus, that's it, you're done. You've finished decaying. So how do we do this? Well, there are three possible ways in which you can decay. Now, these are called particle decays because the process of decaying throws out some kind of particle which has mass. Okay? So these three types of decay are alpha decay, beta decay, and electron capture. Now, this diagram here kind of shows you what happens to elements when they essentially try to decay. So if we look here, so we have increase in proton number on the bottom, okay, and we have increase in the number of neutrons coming up here on the left. Okay. Now these black squares here represent the stable isotopes, the ones that will not decay. So they're good. Now as soon as you go above this line, these isotopes are going to decay through what's referred to as beta negative decay. That's beta decay here. Okay. So in the case of beta decay, you are essentially what is the case of beta decay? You are changing a neutron into a proton. Sorry, I'm having a moment of complete forgetfulness. So in the case of beta decay, you're turning a neutron into a proton. So in that case, what's happening is your nucleus is trying to pull itself into a smaller and smaller and smaller space. So what you do is you take a neutron, which is essentially neutral in charge, and you turn it into a proton, which is positive in charge. Well, by adding a proton, essentially you've increased the amount of electrostatic repulsion, and so instead of your nucleus trying to make itself get smaller and smaller and smaller, the extra proton is going to essentially make it want to expand, isn't it? So it's going to help to achieve balance. So these isotopes up here are going to want to decay through beta negative decay, otherwise known as beta decay. On the lower side of this line of stable isotopes, we have the elements that will decay through beta positive decay. So that is when our nucleus essentially turns a proton into a neutron. So in this case, what we have is a nucleus which is trying to pull itself apart because the electrostatic repulsion is too large. So what do you do in that case? Well, in that case, you take one of the protons and you turn it into a neutron. And once you've done that, the strength of the electrostatic repulsion is decreased, and hopefully you'll be able to achieve balance. Now, right up here at the top, as you can see, we have all these elements which are yellow, and those are the ones which will decay through alpha decay. Okay, you'll notice the ones that decay through alpha decay tend to be very, very large. Okay, so that's going to be elements like uranium, plutonium, and thorium. Okay, these are very, very large isotopes. Now, the final thing to note is that alpha decay, beta decay, and electron capture will all throw out a particle that has mass. There is another type of radioactive decay which you'll be very, very familiar with, especially if you read comic books like the Hulk. Okay, and that is gamma decay. Okay, now the thing is gamma decay will kick out a gamma ray. It will not kick out which does not have mass. Okay, So gamma decay does not produce a particle that has mass, therefore it is not a type of particle decay. Alright, so now after the previous slide where I completely mucked up the types of decay, let's just go through them now. So here we have our three types of decay. Alpha decay, beta decay, also referred to as beta negative decay, and electron capture, which is referred to as beta positive decay. Alright, so what's happening in these three examples? So here is our nucleus. So in the case of alpha decay, our nucleus simply goes, I need to essentially lose some mass. And so our nucleus goes, right, I'm going to kick out 2 protons and 2 neutrons. Bang, off you go. And this process of kicking out 2 protons and 2 neutrons is referred to as alpha decay. And this particle, this 2 proton, 2 neutron particle, is referred to as an alpha particle. So what's going to happen to our nucleus? Well, obviously, because we've kicked out a particle that contains 2 protons and 2 neutrons, the atomic mass of our nucleus is going to go down by 4. 1, 2, 3, 4. The proton number of our nucleus is going to go down by 2, because we got rid of 2 protons, didn't we? 1, 2. So this is alpha decay. Simply, it's a nucleus just going, right, bang, go away, I don't need you. And so that's the process of alpha decay, where it kicks out an alpha particle, which contains 4 particles, of which 2 are protons and 2 are neutrons. Okay. Now the next type of decay is beta decay. So in the case of beta decay, what we're going to do is we're going to take a neutron, a neutral particle, and we're going to turn it into a proton, a positively charged particle. Okay, so a neutron by its very nature is neutral, therefore it has a positive and negative charge which balance each other out. So as soon as you take your neutron and you turn it into a proton, well, that negative charge has to go somewhere, and it's kicked out of the nucleus in the form of an electron. Remember, electrons have mass. Okay, so in the case of beta decay, we take a neutron, we change it to a proton, and in the process we kick out an electron. So what's happening in this case? Okay, well, what's happening to the atomic number? Well, obviously, we have now added a proton, haven't we? So the atomic number has gone up by 1. So the element has changed. It's a new element now. Remember, when the proton number changes, the element changes. The atomic mass, on the other hand, hasn't changed at all, because all we've done is we've taken one neutron, and we've turned it into 1 proton. We haven't really lost anything, have we? So in this instance, the atomic mass remains exactly the same. So what about electron capture? Well, in the case of electron capture, we have a proton which gets struck by an electron. So you have a positive charge plus a negative charge. Well, obviously they cancel each other out, and you end up with a neutron. So in the case of electron capture, we lose a proton and we gain a neutron. So once again, this means the atomic mass doesn't change, because we haven't lost anything, have we? It does, however, mean the number of protons decreases by 1. So once again, we're going to get ourselves a new element, aren't we? Because we've changed the number of protons. And although it's not shown here, this change from a proton to a neutron will kick out a particle called a positron. Okay, that'll get kicked out, and that's the particle that has mass. All right. So you can see we have these 3 different types of radioactive decay, and they will change they'll change the nucleus in different ways. Okay. Now, please learn this bit. Okay. Because there is a super high probability that this will turn up on an exam in the future. All right. So please take some time, learn this. Okay. This is a good place to stop. So pause the video here, please. well, stop the video, should I say, go and get yourself a glass of water, tea, coffee, have a walk around, have a snack, and then come back when you're ready.